Hello all, welcome again. Please subscribe to our channel if you did not subscribe by clicking subscribe button and press bell icon for your personal notifications. If you like this video, please like it after you carefully listen to it. So this is a series of Stm32H7 tutorials, and in memory section now the next topic is FMC, that is flexible memory controller. So in this we will see the overview of FMC supports, key features of flexible memory support, and supported devices, FMC Bank memory mapping, and NOR or PSRAM address mapping, NOR or PSRAM interface signals, NOR or PSRAM timing configuration, NAND address mapping, NAND interface signals, NAND configuration, NAND timing configuration, interrupts, SDRAM address mapping, SDRAM interface signals, SDRAM configurations or SDRAM multibank access, as well as SDRAM optimized class access, SDRAM low power modes, SDRAM commands, SDRAM initialization procedure, low power modes, and application examples and related peripherals used in this context. So FMC controller integrated in Stm32H7 products provides the external memory support through three memory controllers: NOR flash or PSRAM controller, the SDRAM controller, and the NAND memory controller. This enables the CPU to communicate with external memories including NAND and NOR flash memories, PSRAM, SRAM, and SDRAM. The interface is fully configurable, allowing easy connections with external memories or other parallel memories. The benefit of FMC controller not only includes RAM and flash memory space extension, but also ability to interface seamlessly with the most LCD controller, which supports Intel 8080 and Motorola 6800 modes. This LCD parallel interface capability makes it easy to build cost-effective graphic applications using LCD modules containing embedded controllers or high-performance solutions using external controllers and with a dedicated accelerations. Let's quickly look at some of the key features. FMC offers 4 independent banks to support external memories. Each bank has an independent chip selection and chip select and an independent configuration. Each bank features programmable timings, configurable 8, 16, 32-bit data bus, and can access memory in asynchronous mode or burst mode for synchronous memory such as NOR flash and PSRAM. Synchronous memory can be NOR flash and PSRAM. Synchronous memory can be accessed at a maximum frequency of H clock divided by 2. So FMC supports a wide variety of devices, interfaces, and memories. It interfaces with static memory mapped including static RAM access memory, SRAM, read-only memory, ROM, NOR or one NAND flash memory, and PSRAM. The FMC also interfaces with NAND flash memories and supports ECC, that is error code correction, for up to 8 kilobytes of data read or written. 3 interrupt sources can be configured to generate an interrupt when a rising edge, falling edge, or high level is detected on NAND flash ready or busy signal. It also interfaces with synchronous DRAM, that is SDRAM memories. So flexible to adopt various LCDs like Intel 80 and 6, Motorola 6800 modes. Let's have a quick look at FMC Bank memory mapping. The external memories are divided into 4 fixed bank size of 256 megabytes each. 4 external memory banks are dedicated for FMC. Bank 1 is connected to NOR or PSRAM controller. Bank 2 is used for SDRAM bank remap, and Bank 3 is connected to NAND flash. Bank 4 is reserved, and Bank 5 and Bank 6 are connected to SDRAM. So let's look at NOR or PSRAM address mapping. So Bank 1 is used to address up to 4 external NOR or PSRAM memories. You can see in this representation. This bank is split into 4 NOR or PSRAM sub-banks of 64 megabytes, each with 4 dedicated chip select to interface with. 8 or 16-bit asynchronous or synchronous NOR flash is multiplex or non-multiplex mode. 8-bit or 16-bit synchronous or asynchronous SRAM or ROM. 8 or 16 or 32-bit synchronous or asynchronous CRAM or PSRAM memories. So NOR or PSRAM interface signals. FMC outputs a unique chip select signal to each bank and performs only one access at a time to an external device. The external memories are connected to NOR PSRAM controller or NAND controller and share address, data and control signals. You can see in this figure. Okay, next we can move on to the timing configuration. NOR PSRAM controller allows configuration of various timing parameters for supported memories: address setup phase, address hold phase, and data setup phase, bus turnaround phase, clock divide ratio. I need to talk about clock divide ratio. Number of AHB cycles H clock within one memory cycle, that is CLK, and data latency, number of clock cycles to be issued to the memory before the first data transfer access mode. Let's jump on to NAND address mapping. Bank 3 is used to interface with the NAND flash memory. It is divided into two memory spaces: common memory space and attribute memory space. Both spaces are similar. The common memory space is for all NAND flash read and write access except when writing to the last address byte to the NAND flash device, where the CPU must write to attribute memory space. This allows to pre-wait functionality needed by the certain NAND flash memories by writing last address byte with different timings. Each memory space is subdivided into 3 sections: data section 64 kilobytes used to read or write data from NAND flash memory; common section, that is 64 kilobytes used to send command to NAND flash memory; address section, that is 128 kilobytes used to specify the NAND flash memory. Is this clear? Let's move on. Can we move on to the interface signals of NAND flash, NAND interface? Yeah, go through this, then we will move on to the FMC generates the appropriate signals to drive NAND flash memory. The address, data and control signals are shared with the NOR or PSRAM controller. The command latch enable CLE and address latch enable ALE signals from the FMC controller connected to address line 16 and address line 17 respectively. The ALE is active when writing to the address section, and the CLE is active when writing to the command section. So how about configuration? So FMC NAND memory controller includes support for the following features like ECC, error code correction. This algorithm can perform 1-bit error correction and 2-bit error detection per 256 to 8192 bytes read or write from or to the NAND flash memory. It is based on the Hamming code algorithm. Three interrupt sources can be enabled to detect a rising edge, falling edge, or level on ready or busy signal output from NAND flash memory. Wait feature management. The controller waits for NAND flash memory to be ready before starting a new access. The MPU memory attribute of the FMC NAND bank must be configured as a device. So coming to the timing configuration, each common and attribute memory space can be configured with different timings for NAND flash command, address write and data read or write access. The attribute memory space is used for the last address write access if the timing must differ from that of previous access in case of ready or busy management. Otherwise, only common space is needed. 4 parameters are used to define the number of HCLK, H clock cycles for the different phases of any NAND flash access. Setup time, wait time, hold time, data bus, his time are the 4 parameters. Now let's see at interrupts with the rising edge, falling edge and high level. 3 interrupt sources, right? So FSMC INT pin on detection will, when it is connected to the ready or end busy signal for the NAND flash memory. Let's move on to the SDRAM address mapping. Bank 5 and 6 are used, as we discussed earlier, to interface with the SDRAM memory. Each bank can address up to 256 megabytes of memory. 2 banks can be used to interface with 2 SDRAMs. You can see it here. Type it here. Yeah. And coming to the SDRAM interface signals, you need to note down the difference between the NOR and now the SDRAM. FMC generates the appropriate signal to the drive SDRAM memory. The address and data are shared with NOR or PSRAM controller. Okay. I'll come on to that. The bank address signal FMC BA0 and FMC BA1 are shared with FMC A14 and FMC A15 respectively. Is this clear? I hope I answered your question. Okay. Right. The SDRAM controller has dedicated signals like SD clock. Please look at the diagram carefully. SD clock, SDCLC, that is SDRAM clock, SDCKE0, that is SDRAM Bank 1 clock enable, and SDCKE1, that is also Bank 2's clock enable, SDNE0, that is chip enable of Bank 1, SDNE1 is chip enable of Bank 2, NRAS is row address strobe, NCAS is column address strobe, SDNWEN is write enable. Okay, copy it here. And then we can move on to the SDRAM configuration we just saw. We are going in the same sequence as we went with the NOR. Okay, FMC controller offers 2 independent SDRAM banks to support separate external memories. Each bank has an independent chip select and an independent configuration, as we discussed earlier. I'm just reminding it here. Each SDRAM bank can support memory devices up to 13 bits for address row and up to 11 bits for address column. SDRAM can be accessed at the maximum frequency of H clock divided by E. Each bank features programmable timings and a configurable 8, 16 or 32-bit data bus. So the question comes here, how can I have a multi-bank access? Yes, it supports multi-bank access. Multi-bank ping-pong access allows to perform consecutive write access to different banks. Consequently, it avoids bank pre-charge and row activation when the row is already activated in Access Bank. So what about optimized access? So cacheable read FIFO, first in first out, with depth of 6 32-bit lines. Configurable read burst allows to anticipate the next read access during CAS latencies, which is an advantage. Okay, for optimized access. And coming to the low power modes, two low power modes are supported. One is self refresh mode and the second one is power down mode. So SDRAM controller adds a cacheable read FIFO, first in first out, with a depth of 6 32-bit lines. The read FIFO is used when the read burst is enabled and allows to anticipate the next read during the CAS latencies. You can quickly note down the point. Anyways, I'm typing it here, the SDRAM controller. Okay. If these modes are clear to you, you can see, yeah, that was given in this. Yeah, SDRAM device is selected, read or write operation requested are set to 000, that is normal mode now. Okay. Can we move on to SDRAM commands? Yep. For energy saving, the SDRAM controller can be configured in one or two low power modes. Self refresh or power mode. When we saw, when in self refresh mode, the SDRAM retains data without external clocking. The device can remain in a self-refresh mode as long as requested by the application. The device can remain in self-refresh mode when a SDRAM device is selected read or write mode, which I already discussed. The device cannot remain in the power down mode. So here you can see command and mode bits. So normal 000, clock configuration enabled 001, and PLL, that means all bank pre-charge command 010, and auto refresh command is 011, and load mode register LMR is 100, self refresh command is 101, and power down command is 110. Is this clear? Yeah. That is configure target bank bits CTB1 and CTB2 in FMC_SDCMR. Fine, we can look at it when we are writing a project over here. I prefer STM32 Cube IDE than any other third parties. Nowadays, STM Cube IDE is picking up to all the ecosystem standards, everything. It is more or often like an Eclipse or IAR embedded workbench. It's much better nowadays than IAR embedded workbench. Procedure, yeah, I'm following. I'll just, after this, we'll follow with SDRAM initialization procedure. Fine. Yeah. So, SDRAM controller can issue different commands to the SDRAM devices. The commands are issued by software to initialize the SDRAM device or to switch the device mode. Here is the procedure I have given. The commands can be delivered to the two banks simultaneously using configure target bank bits CTB1 and CTB2 in FMC_SDCMR registers. Yeah, I'll come up with a table in the next sequence. Surely you just go through these procedures. Copy it and I'll come up with a table for that. It's that low power modes is quite common. In most of the cases it would be like run is sleep is active, peripheral interrupts cause the device to exit sleep mode. The same stop, here it comes. See, the on standby mode, it's obvious the peripheral must be reinitialized after exiting domain and system standby mode. The slide represents the SDRAM initialization procedure to implement it firmware. Nothing much. Here now I'll come up with application examples. Carefully look at this application: LTDC, I2C touch panel, FMC, I2C, quad SPR NOR flash on the left, which was been represented in gray. FMC is active in run and sleep modes, as the previous table shows. A FMC interrupt can cause the device to exit sleep mode. To retain external SDRAM memory while in stop or standby modes, it can be put in the self-refresh mode prior to entering stop or standby modes. I recommend this technique. It worked for me plenty of times. If you go through some peripherals like reset clock control, RCC and NVIC and general purpose IOs, which are the trainings will be followed soon, so those things will help you. Okay, anyways, thanks for your time, and if you like this particular session, please press or click like button. If you did not subscribe to our channel, please subscribe to our channel. Thank you.